This is a question from AQA A-level Chemistry. It is a required practical question from paper 3, and this one is based on RPA8. As always, I'm going to recommend you pause, have a go at each section, and then review your answers in the remainder of the video. So here is the entire question, A through to E. And if we take a look here, we've got a biocide, a chemical that is used to kill bacteria. A biocide is added to prevent the growth of bacteria in the water used in vases of flowers. Household bleach contains aqueous chlorine and can be used as the biocide. The concentration of chlorine in vase water decreases with time, and it was decided to investigate the rate of this decrease. The following experimental method was used to determine the concentration of chlorine at different times. A sample of vase water was taken, an excess of Ki solution added to the sample, the chlorine in the sample oxidized the I- ions to I2, the iodine is then titrated with sodium thiosulfate, and that's repeated again and again using further samples taken at hourly intervals. So for part A, suggest 2 reasons why the concentration of water of chlorine in the vase water decreases with time. Well, the first one, we've got to think about why the bacteria is there, and the bacteria is interacting with the bacteria. So it's used to kill the bacteria, which means it's no longer there. The second option that we've got here is actually even more simple. It might be it's just evaporated away. Now, you only need 2 reasons here, but there are more to choose from. The third option that we have is that if you remember the reactions of chlorine with water, depending on the presence of UV light or not, you will know that it will react with water to form HCl and O2. That's going back to the group 7 topic. Okay, on to part B. Suggest why this sampling technique has no effect on the rate at which the concentration of chlorine in the vase water decreases. Well, the concentration of the remaining solution is unchanged. So for that reason, it isn't going to have an effect. Part C, why was it important to use an excess of potassium iodide solution? Well, we wanted to make sure that all of the chlorine had reacted, and that was the way to do that. On to part D. Use the following standard electropotential data to explain why iodine oxidizes S2O32- under standard conditions. And we've got our 2 half cells both showing reduction as they always do, and our E cell values. I'm going to use the method that you'll see on all of my videos. I'm going to draw the number line, and I'm going to put my smaller value or least positive on the left, my most positive on the right, and I'm going to identify what those 2 half cells are. Once I've done that, because the number line is always drawn in this way, we know that electron flow is always going to be from the left-hand side to the right-hand side. You can think about that as being a negative electron going towards the more positive, if that helps you to remember it. So the electron flow goes in this way. And what that actually means is that the S2O32- half equation needs to be reversed. We've been given the reduction and we need the oxidation. So the iodine is on the right hand side, or it is the more positive E cell value. I've done a lot of work there to build up to that, but I think building the understanding and recognizing why rather than trying to remember as fact is probably beneficial. Finally, deduce an ionic equation for the reaction between I2 and S2O32-. So you've already been signposted here actually to the fact that the second half equation here is the one that's reversed, because we're starting with the thing on the right hand side. Well, we reverse it, and that takes us to what we have here. We don't need to multiply up because we've got 1 electron on each side of the equation, which means we can remove them as spectators. So we're looking for S2O32- plus half I2 goes to half S4062- plus I-. Multiples of that would be absolutely fine as well. That takes us to the end of this question. Thank you for listening, and goodbye.